So hello, I'm Shrija Ghosh and I'm PMRF from IIT Kanpur, and this is the sixth week of the problem solving session for the course Environmental Chemistry and Microbiology. The course instructors for this course are Professor Anjali Pal and Professor Sudha Goel. So today I'll be discussing the different questions related to radioactivity part. So feel free to ask any questions. I'll start with the questions now. So the first question is, among alpha, beta and gamma particles, which one has the highest penetrating power? Option A is alpha, option B is beta and option C is gamma, and all have equal penetrating power. So we have to tell which of these particles have the highest penetrating power. So the answer for this question is gamma particles. So gamma particles have the highest penetrating power. So let's see what are the penetrating power of the other particles. So for alpha particle, the penetrating power is very weak. It is up to 0.01 millimeter of an aluminium foil. So it can penetrate only 0.01 millimeters of an aluminium foil. So that it's very weak, the penetration power of alpha particles. Penetration power of beta particle, it is better than the alpha particle, but it is still poor. It is still 0.1 millimeter of aluminium foil. And the penetration power of gamma particles, it is very high. It is up to 8 centimeters of the lead. So you can see the difference. Here. For alpha particle, it is 0.01 millimeters of an aluminium foil, whereas for gamma particle, it is 8 centimeters of lead. Okay, so it can penetrate with great powers. Okay. So moving to the second question. Emission of one alpha particle results in shift in how many places in the periodic table? So the options are 2 places towards the right, 4 places towards the right, 2 places towards the left, or 4 places towards the left. So what is an alpha particle? First we have to see, if an alpha particle is emitted out of an element, how many places it will get shift, like the product that we will get, how many places it will shift in the periodic table. So what is an alpha particle? Do you know? Do you know what is an alpha particle? Can you answer? So an alpha particle is basically equivalent to the helium nucleus. So helium has the atomic number of 2 and the atomic mass number of 4. That means it has 2 neutrons and 2 protons in its nucleus. Okay, so alpha particle is similar to an helium atom. So if an alpha particle is emitted out of the element, so what will happen? It will shift 2 places towards the left in the periodic table. Why? Because when an alpha particle, it is identical with the helium nuclei. So in an helium nuclei, number of the atomic number is 2. So if an alpha particle, let's say an alpha particle is emitted out of radium and it turns into radon. So from 88, the atomic number is now changing to 86. So it is decreasing 2 times. So it will shift towards the left of the periodic table. And how many places it will shift? It will shift 2 places, because the atomic number is decreasing by 2. Okay. The mass number, whereas the mass number, it will decrease by a factor of 4, because helium, the mass number for helium is 4. So if you see the mass of radium to 226, it decreased to 222, okay, upon an alpha particle emission. Okay, so one alpha particle is emitting, so 2 places will reduce in the atomic number, and the atomic mass number will reduce by 4 places. Okay, if 2 particles were being emitted out, so accordingly it would have shifted 4 places towards the left. Okay, so like that we have to calculate. So basically an alpha particle is equivalent to an helium nuclei. That is one thing you have to remember. Okay. So moving to the next question. Half-life of a radioactive isotope N is 35 years. The half-life is given as 35 years. It decays to another element Y, which is stable. The 2 elements N and Y were found to be in the ratio of 1:7 in a sample of given rock. Age of the rock is estimated to be. So we have an we have the half-life of the radioactive isotope N given as 35 years, and we know that N is decaying to a different element called Y. Okay, now at a given time the ratio of N and Y is found to be 1:7. That means 1 parts of N is present and 7 parts of Y is present. That N has decayed into Y. So 7 parts of Y is present. So we have to estimate the age of the rock. So how will we solve this question? Let's see. So we'll use the formula N is equal to N0 multiplied by 1/2 raised to the power of small t divided by capital T. Now here the capital T is denoting the half-life of the element. It is the T half. Okay. The small t is denoting the age of the element, and your N is the amount of undecayed element that is present, and N0 is the initial amount of element that is present. So now we in the question they have given that N is decaying into Y, and the ratio of N is to Y is 1/7. That means initially we can assume the amount of N that was present, that is N0. Initially it would be N plus Y. Okay, that is 1 plus 7. Okay, I hope this is clear. N is to Y, the ratio is given as 1:7, 1/7. Okay, 1 parts of N is there and 7 parts of Y. Now that 7 parts of Y has come from N, because N is ultimately decaying into Y. So those 7 parts of Y, initially those 7 parts were also present as N. So the initial amount of N present in that rock is 1 plus 7, that is 8. Total 8, the amount, the N0 value for N0 can be equal to 8. Now final amount of N that is present, we can assume it to be 1. Okay, so 1, so N by N0 will be 1 divided by 8. Initial was 8, final is 1. Okay, so 1/10 is equal to 1/2 raised to the power of t, small t divided by capital T. Now if you see 1 by 2 raised to the power of 3 is equal to 1 by 8, because 2 cube is 8, 2 raised to the power of 3, that is 2 cube is 8. Okay, 2 into 2 is 4, 4 into 2 is 8. So 1 by 2 raised to the power of 3 is equal to 1 by 8. So that means small t divided by capital T, that is age of the element divided by its half life, it is equal to 3. Okay. Now in the question, the half life of the rock of the element N is given as 35 years. Okay. So if I have to calculate the age of the rock now, it will be 3 into 35 years, that is 105 years. Okay, I hope this is clear. So you have small t divided by capital T, that is age of the element divided by the half life of the element as 3. Okay, so age of the element is 3 into half life of the element, that is 3 into 35, that is 105 years. So the answer for this question is 105 years, that is option number B. Okay. If there's any doubt in this question, please ask.
Na by NB 1 by 7. That
Yes.
but will you repeat again?
So in the question, if you see, they have given two elements N and Y were found to be in the ratio of 1:7 in the given rock. So in that rock, there is an element called N. That N is decaying into Y. Okay. So at a particular given time, the ratio of N is to Y is 1:7. Okay, so that's why N divided by Y, it is given as 1:7, 1 by 7. Now the initial amount N0 is nothing but, because all the Y, it has come from N only, N has decayed into Y. So this 7 parts of Y, it was also N initially. So initially amount of N would be 1 plus 7. Okay. So Na upon Nb is nothing but the N by Y, the ratio that is given in the question. Okay.
Yes.
Yeah. So Na is the amount of element undecayed, that is N, that is given in the question, and Nb is the amount of element decayed, that is N is getting converted into Y. So that is Y is denoted by Nb. Fine. Sorry. Okay. So this is clear, right? So I'll move to the next question.
Yes, yes.
Yeah. So question number 4. 70% of an radioactive sample is left undecayed after time t has elapsed. What is the approximate percentage of the initial sample will decay in total time 2t? So in time t, 70% of the sample is left undecayed. That means only 30% is getting decayed. Okay. In time t. Now we have to find the percentage that is decayed in time 2t. Okay. So let's see how to solve this question. So we'll use the similar formula. So we have, for any radioactive decay, it follows a formula which is similar to the first order reaction that we studied in the previous sessions. So N is equal to N0 e raised to the power of minus lambda into T, where N is the amount of sample that is remaining, that is undecayed. N0 is the initial amount of sample, and lambda is the decay constant, and T is the time. So at time T, they have said that 70% of the sample was left undecayed. So n, the value of n would be 70% of the n0 initial amount. 70% of the initial amount is left as undecayed. So 70% means 70 upon 100. So 70 upon 100 of n0 is equal to n0 e raised to the power of minus lambda t. Now 70 upon 100 can be written as 7 by 10. So that's what they have written. 7 by 10 n0 is equal to n0 e raised to the power of minus lambda t. Now here n0 will get cancelled out with n0 on the RHS. So we will get 7 by 10 is equal to e raised to the power of minus lambda t. If you take log on both sides and change the sign from negative to positive, you will get lambda is equal to 1 upon t log 10 by 7. Okay, this is natural log base e, because we had e raised to the power of minus lambda t on RHS. So we will convert it into natural log. So 1 by t multiplied by natural log of 10 by 7. Why 10 by 7? Because we had e raised to the power of minus lambda t. So whenever you change the sign in log, your when the factors are in form of when the numbers are in form of factors, the numerator gets exchanged by denominator. So log a by b, if you change the sign from positive to negative, it will be log minus log b by a. Okay, that is fine. So lambda is equal to 1 by t ln 10 by 7. Now we have to find what will be the percentage of the sample at time, after time 2t. What will be the percentage of the sample that decays at time 2t? So at time t we got we have 70% of the sample undecayed. That means 30% decay is happening. At time 2t what will happen? So we have the number of nuclei that decays in t time is n0 minus n. So we have the value of n as n0 e raised to the power of minus lambda t. So if you take n0 as common, it will be 1 minus e raised to the power of minus lambda t. Number of atoms decayed in 2t time would be like it's n dash. N dash would be equal to n0 n0 in common 1 minus e raised to the power of minus 2 lambda t, because it's now t is equal to 2t. So 2 lambda t, okay, or minus lambda into 2t. Okay. So now if I have to find the percentage, how will you find the percentage? Percentage will be n dash, that is the number of atoms decayed in time 2t, divided by the initial amount multiplied by 100. That is how you calculate the percentage. Okay, final divided by the initial multiplied by 100. So we'll just substitute the values. So n0 will get cancelled out from the numerator and denominator. So 1 minus e raised to the power of minus 2 lambda t multiplied by 100. Now we have the value of lambda 1 by t, natural log of 10 by 7. So we will substitute the value of lambda here. So 2 by t ln 10 by 7 multiplied by t. So now once you solve this, once you solve the whole thing, you will get this value. So since it is e raised to the power of log 10 by 7, it will be, and this log is also in base e, so it will be 10 by 7. So minus 2 by t into 10 by 7, and this minus 2 is in the power of e, so it will go in the power of 10 by 7. So it will, so once you solve this whole thing, t will get cancelled out with t. So 10 by 7 raised to the power of minus 2. So it can also be written as 7 by 10 raised to the power of 2. So 1 minus 7 by 10 raised to the power of 2 into 100. Now 7 by 10 is 0.7. 0.7 whole square means 0.49. 7 sevens are 49. So 0.49. So 1 minus 0.49 is 0.51. 0.51 into 100 is 51%. Okay. So you just have to solve this whole thing. Once you solve this, you will get the answer to be 51%. So option number B for this answer is correct, 51%. Okay. So 51% of the initial sample will decay in after time 2t. Okay. I hope this calculation was clear. Let me know if there is any doubt. Otherwise, I'll move to the next question. Okay. So the next question is, by how much the average life is greater than the half life? So half life of an element and average life of an element, what is the relation between them? And by how much factor it is greater than the half life? Okay. So how to solve this? Now we know that half life is equal to T half is equal to 0.693 divided by lambda. Okay. And average life is inversely proportional to lambda. So average life is equal to 1 by lambda. Okay. So average life is equal to 1 by lambda. Now 1 by and lambda can be written as T half divided by 0.693 divided by T half. Lambda can be written as 0.693 divided by T half. So if I divide it by 1, so 1 by lambda, so that means 1 divided by 0.693 divided by T half. So if you solve this thing, so T half will go in the numerator. So T half divided by 0.693. So that means, and 1 divided 0.693 is 1.44. So average life is equal to 1.44 times T half. So average life is 1.44 times greater than the T half, that is half life. Okay. So the correct answer for this question is option number A, 1.44 times. Okay. So average life is 1.44 times greater than the half life of an element. This is clear?
Yes.
Yeah. So now I'll move to the next question. Calculate 7.5 into 10 raised to the power 10 disintegration per second to becquerel units. So what is becquerel units? First we have to see. So 1 disintegration per second is equivalent to 1 becquerel unit. Okay. So 1 disintegration per second is equivalent to 1 becquerel unit. So now 7.5 into 10 raised to the power of 10 disintegration per second will be equal to 7.5 into 10 raised to the power 10 becquerel units. So the correct answer for this question is option number A, 7.5 into 10 raised to the power 10. So it will remain same as the disintegration per second. Okay. So 1 disintegration per second is equal to 1 becquerel unit. So disintegration per second and becquerel units are equivalent to each other. Okay. So the answer will remain the same as the number of disintegrations per second, that is option number A, 7.5 into 10 raised to the power of 10. So question number 7. Which of the following series is denoted by 4n plus 3? So we have 3 series given: actinium, thorium and uranium. So we have to see which of the following series is denoted by 4n plus 3. How this 4, what do you mean by 4n plus 3? So n is basically the atomic mass number. If you divide the atomic mass number by 4, so if it is completely divisible by 4, it will be 4 into n. If it has 1 as in the remainder of the division, so it will be 4n plus 1, 4n plus 2, 4n plus 3, like that. So in the following series, actinium, thorium and uranium, actinium is actually denoted by 4n plus 3 series, thorium is denoted by 4n and uranium is denoted by 4n plus 2. Okay. So the mass number for actinium is 227. The mass number of thorium is 232. So that's why it is denoted as 4n. So if you divide 232 by 4, it will be completely divisible. So it will be, that's why thorium series is denoted by 4n. But if you divide 227 by actinium, it will be 4n plus 3 series. Okay. So like that, it is denoted. So uranium is 4n plus 2 series. So we'll move on to the next question now. Question number 8. A uranium ore contains 10.2 grams of uranium 238 and 9.2 grams of lead 207. So uranium decays into lead. Okay. So calculate the approximate age of the ore. Given the molecular weight of the uranium and lead are 238 and 207 respectively, and half-life of uranium is equal to 4.5 into 10 raised to the power of 9 years. So now in this question we have an ore in which uranium is present, and this uranium is getting decayed into lead. Okay, uranium is decaying into lead, and at a particular and we have to calculate the age of the ore. At a particular time, the amount of uranium and lead is given. So the amount of uranium is 10.2 grams and lead is 9.2 grams. Okay, so it's similar to the previous question where the ratio was given and we had to calculate the age of the rock. It is very similar to that question. In this question, we have the half-life of uranium given as 4.5 into 10 raised to the power of 9 years. So let's see how we'll solve this question. First, we can calculate the lambda, the decay constant. So since the half-life is given as 4.5 into 10 raised to the power of 9, so lambda will be equal to 0.693 divided by T half. This I have told you. So lambda is equal to 0.693 divided by 4.5 into 10 raised to the power of 9. So that is equal to 0.154 into 10 raised to the power of minus 9 per year. So the decay constant, unit of decay constant is per unit time. So per year. Now what is the amount of uranium and amount of lead present? So they have given it in grams. So we have to calculate the number of moles, because whenever you are writing any reaction or any equation, you always consider the moles Okay, so now here also 1 mole of uranium decays into 1 mole of lead. So we will calculate the number of moles from the amount given. So the amount of uranium given is 10.2 grams, and the molecular mass of uranium is given as 238. Okay, 238 is the atomic mass number. So given mass upon the atomic mass, that is 10.2 divided by 238, that is 0.043 moles of uranium. Okay, so 10.2 grams of uranium is equal to 0.043 moles of uranium. Now similarly we will calculate the number of moles of lead. So we have 9.2 grams of lead, and the atomic mass number for lead is 207. So 9.2 divided by 207 is equal to 0.044 moles of lead. Okay, so 9.2 grams of lead is equal to 0.044 moles of lead. Okay, so now 0.43 moles of 0.043 moles of uranium is present, and 0.044 moles of lead is present. That means initially what was the amount of element present? So uranium is only decaying into lead. Okay, so the amount of lead that is present currently, it was also uranium once upon a time. So 1 mole of uranium is gets converted into 1 mole of lead. So 0.44 moles of lead was once 0.044 moles of lead was once 0.044 moles of uranium at the beginning of the ore. Now we have to calculate the age of the ore, right? So we need the initial amount of the element that was present. So 0.043 plus 0.044, that is 0.087 moles initial moles were present, okay, for uranium. The final moles of uranium is 0.043. So log n0 upon n is equal to lambda t. This is similar to the formula that we are using till now. So n is equal to n0 e raised to the power of minus lambda t, right? So if you divide it, if you take log both sides, it will be log n is equal to log n, it will be equal to log of n is equal to log of n0 into minus lambda t, or you can take the reverse of it. So log of n0 divided by n is equal to lambda t. Okay, so n0 is 0.087, n is 0.043. So ln, that is natural log 0.087 divided by 0.043 is equal to, now the value of lambda we have calculated, decay constant we have calculated from the half life. So 0.154 into 10 raised to the power of minus 9 multiplied by t. T is the time period, time that has taken to decay from 0.087 to 0.043 moles. Okay, so that is the age of the rock, because at the beginning we have calculated the number of moles of uranium. So T will denote the age of the rock, that how old that ore is or the rock is. So if you solve this whole thing, log of 0.087 divided by 0.043 and then divide the final answer with 0.154 into 10 raised to the power minus 9, you will get the value of T to be 4.6 into 10 raised to the power of 9 years. Okay, 4.6 into 10 raised to the power of 9 years, that is the final answer. that is option number B is the correct answer. 4.6 into 10 raised to the power of 9. Okay. So for such type of questions, when you have to calculate the age of the rock or age of the ore, whatever ratio of the amounts is given, if it is given in form of ratio, then directly you can calculate from that. If it is given in terms of grams, you have to calculate the moles. Since all the reactions, the amount is considered in terms of moles, so you have to calculate the moles, okay, the concentrations of the moles. So once you calculate the moles, or once you have the molar ratio, you can just find the initial amount and then substitute in the formula used to formula from n is equal to n0 e raised to the power of minus lambda t. Lambda, you can, if the lambda value is given, well and good. If the lambda value is not given, if the t half is given, you can always calculate decay constant from half life, and you can calculate half life from decay constant as well. So you can solve such type of questions like that. Whatever values are given, you can just put in the formula and you can find the unknown. Okay, I hope this question was clear. I'll move to the next question. Let me know if there's any doubt.
Yes. No, it is clear.
Yeah, okay. So, question number 9. The decay constant of a radioactive element is 0.0223 day inverse per day. Okay. Find the half-life approximately. So, right now only I have told you how to solve half-life from decay constant and how to solve decay constant from half-life. So, it's very simple. So, decay constant is equal to 0.693 divided by half-life. So, the decay constant is given. So, it will be, the half-life will be equal to 0.693 divided by decay constant. So, half-life is equal to 0.693 divided by lambda, that is equal to 0.693 divided by 0.0223. If you solve this, you will find the answer to be 31 days. Now, your decay constant was in the unit of day inverse, so that will go to the numerator, so it will be days. Okay, the unit will be days, so 31 days. So, the correct answer for this question is option number C. Okay, so the decay constant is given, the half-life for this element would be 31 days. Okay, option number C. This was very simple. Okay, so the next question, question number 10. The C14 to C12 ratio. So, what does this 14 and 12 representing? It is the atomic mass number. So, the atomic number is same. Atomic number for both the carbon is 6. It is carbon, so the atomic number will be fixed 6. Mass number, however, it changes depending on the number of neutrons and protons in the nuclei. Mass number is nothing but the sum of the neutrons and protons. Okay, so in C12 the number of neutrons and protons are equal. In C14 the number of neutrons are higher than the number of protons. So the ratio is given for C14 to C12. C14 to C12 ratio in a piece of wood is 16% that of the atmosphere. Okay, the ratio is given as 16% that of the atmosphere. Calculate the approximate age of the wood. So again, it's the similar question. You have the ratio given, you have the T half given, so you can find the decay constant from the T half first, and then you can calculate the initial amount of the element, and then you can calculate the age. So let's see how to solve this. So you have the T half given. So decay constant will be equal to 0.693 divided by T half. So 0.693 divided by 5580 years. 5580 years is the half life of this carbon element. So 0.693 divided by 5580, it will be equal to 1.242 into 10 raised to the power of minus 4 year inverse. So per year. Okay, so lambda, value of lambda is 1.242 into 10 raised to the power of minus 4. So now lambda can be written as 2.3. So now they have written the solution in terms of log base 10. So when you have to convert from natural log to log base 10, log base e to log base 10, you multiply by a factor of 2.303. So if it was ln, that is natural log, it would have been 1 by t ln C0 by Ct or N0 by N. So in this case it is 2.30, they have multiplied it by 2.303. So 2.303 divided by t log base 10 of C0 by Ct or N0 by N, whatever you write. So in C0 is the initial. So initial, if it let's assume the initial amount was 100%. So they have said it is 16% of the initial. So 16% means if it was 100, so that means the final will be 16. Okay, and T is the age of the wood. So now lambda, value of lambda is calculated as 1.242 into 10 raised to the power of minus 4, which is equal to 2.303 divided by T multiplied by log base 10 100 upon 16. Okay, 100 upon 16 is 6.25. So T will be equal to 2.303 divided by lambda, that is 1.242 into 10 raised to the power of minus 4, multiplied by log base 10 of 6.25. Okay, so when you solve this whole thing, so log 6.25 is 0.796, and when you multiply the, when you divide 2.303 into 2.303 divided by 1.242 and then multiply it by 0.796, the approximate value would be 14,758 years. So this will be the age of the wood. Sorry. So the age of the wood is 14,758 years. Okay, so option number B is the correct answer.
Would you please repeat from line 3?
Line 3. Lambda is equal to 2.303 divided by T log 10 by C0. This, right?
Yes, yes.
Yeah. So what is the doubt you have? It's the same
In that
formula.
equation, previously it was lambda equal to 1 by t ln n0 by n.
Yes. So
So,
yeah, yeah, I'll tell you. So when it is 1 by t ln n0 by n. So C0 and, like, here I have written C in place of n. So you consider it as n0 by n only. When you convert ln to log, when you write log, okay, so that means that is with base 10. Okay, log base 10. When you write ln, it is in the base of e. Okay, exponential e. So when you convert ln into log, you have to multiply it by 2.303. 2.303 is a factor. So 1 by T ln C0 by Ct is equal to 2.303 by T ln log C0 by Ct. So basically log x ln x is equal to 2.303 log x. Okay, is that clear? Ln x is equal to
Yes, yes.
2.303 multiplied by log x. So 2.303 is just the factor that is multiplied to convert it in terms of log. Okay, rest of the formula is same. So n0 is the initial, where in this case we have written it as C0. It is the same as n0. So n0 is the initial and nt is the final, or n is the final. So initial we have assumed it to be 100%. So because in the question they have said 16% of the initial. So if the initial is 100, then the final is 16. Since it's in ratio, you can assume the initial to be 100 and the ratio will be same. Okay, if the initial was some x also, so the final will be 16% of that x, right? So the ratio will be same. So you can assume the initial to be 100 and the final is already given as 16. Rest of the formula is same. You just substitute the values to solve for T. I hope this is clear now.
Yes, it is clear.
So I'll move on to the next question. Just a second. So question number 11. Identify the type of emission in the following reaction. So lead, the mass number is given as 210, atomic number is 82. It is converting into Bi, the mass number is remaining the same, the atomic number has increased by 1. Okay, so the type of emission, the type of particle that is being emitted out of this reaction, we have to identify. So is it an alpha emission, beta emission, alpha emission followed by beta emission, or beta emission followed by alpha emission? So I have told you in the first question itself what was alpha particle. Alpha particle was equivalent to an helium nuclei. So in an alpha emission, the atomic number decreases by 2 and the atomic mass decreases by 4. So in this case, if it was an alpha emission, your 82 would have become 80 and 210 would have become 206. But your 82 is increasing. So in a beta emission, what happens? Beta is similar to an electron. So beta, once beta is emitted, electron is emitted. If electron is emitted, one positive charge will increase. If you increase one positive charge, that means what is positive in an atom? You have electrons as the negative components, and the positive component for an atom is protons. Okay, so the atomic number is nothing but the number of protons. So if an electron is released out, the atomic number will increase. Okay, so if one beta emission is happening, that means the atomic number will increase by 1. Okay, so this is a type of beta emission that is happening. The answer is B, option number B. Beta particles are nothing but they are similar to electrons. Okay, so if an electron is released out, positive charge will increase and thus the atomic number will increase. So if it is asked like in the periodic table, where will the new element shift? Will it shift to the right of the periodic table or left of the periodic table? The answer will be to the right of the periodic table, and by how many places? By one place. Okay, because from 82 the element is changing to 83, so it is going to the next box, basically next box to its right. Okay, moving one step forward. I hope this is clear. I'll move to the next question. Question number 12. After which atomic number all nuclei become unstable? So, atomic numbers are generally denoted by Z and atomic mass are generally denoted by A. So, after which atomic number value all nuclei become unstable? So, when does a nuclei become unstable? When the neutron to proton ratio is starts increasing more than 1. Okay, generally for the atomic numbers, for the elements with atomic numbers, smaller atomic numbers, which are at the beginning of the periodic table, the number of neutron is equal to the number of protons. So, you have seen carbon 12, C12, the atomic number is 6. So, that means it has 6 protons and 6 neutrons. So, proton plus neutron, 6 plus 6 is 12. So, that is why the atomic mass number is just the double of the atomic number. But when you go higher up in the periodic table, when you go with to the elements which has a higher atomic number value, you will see the neutron to proton ratio deviates from 1. So, it will increase, so it will have more number of neutrons than the number of protons, and thus the nuclei becomes unstable. It tends to release those neutrons or protons from the nucleus. So, the nucleus tends to break or it can fuse. So, it can undergo certain radioactivity, it can undergo radioactivity. So, after which atomic number value all nuclei become unstable? The answer is 83. So, after 83, what happens? If you see in this plot, so if you see the plot for 1:1, like the number of neutron is equivalent to the number of proton, the graph is straight line. But actually what happens as we go, as the number of protons increases, as the atomic number is equal to the number of protons. Okay, so that as the number of proton increases, the number of neutrons are not equal to the number of protons, they start increasing furthermore. So, if you see after 83, the number of neutrons are much more higher than the number of protons. The ratio of number of neutrons, n is to p, that ratio is very higher than 1. So, once it becomes very higher, very larger than 1, the nuclei becomes unstable and it undergoes radioactivity. Okay. So, all the elements having the atomic number value of more than 83, their nuclei becomes very unstable, because the number of neutrons are not equal to number of protons, they are much larger than the number of protons. Okay. I hope that was clear. So, question number 13. Which of the following rays used for gammaxine synthesis? So, gammaxine synthesis, it is which of the following rays is used for the synthesis? So, the answer is gamma rays. So, it is in the name of the compound also, gammaxine. It is called gammaxine because gamma rays are used for the synthesis of this. What is it exactly? It is actually a pesticide. It's a pesticide. The chemical name for the pesticide is hexachlorobenzene. So, you have a benzene with chlorine substitution on all the 6 carbons. Okay, hexachlorobenzene. So this hexachlorobenzene, it is synthesized from benzene and chlorine by gamma irradiation. Okay, so benzene and chlorine, they are irradiated by gamma rays to form gamaxine. Okay, and gamaxine is used as a pesticide. Okay, so that's why we call it gamaxine, because it is synthesized from benzene using gamma rays. Okay, so benzene, the ene from the benzene and gamma from the gamma rays. Okay, gamaxine. So it is nothing but hexachlorobenzene. So hexachlorobenzene is the chemical name for this compound. Okay, so moving on to the next question. Question number 14. What is meant by nuclear transmutation? Okay, so now what is meant by nuclear transmutation? Option A is transformation of one nucleus into another. Option B is splitting up of one nucleus into two parts. Option C is combination of two nuclei to form a new nucleus. And D is none of the above. So nuclear transmutation, it is actually transformation of one nucleus into another. The answer is option number A, transformation of one nucleus into another. The option number B, splitting up of one nucleus into two parts. Do you know what it is called? Splitting up of one nucleus into two parts. Do you know what it is called? It is also called a phenomena. Do you know the name of that phenomena? Any idea? Splitting up of one nucleus into two parts, it is called nuclear fission. Okay, it's a radioactive reaction only. So one nucleus splits into two different nuclei. So it is called nuclear fission. And combination of two nuclei to form a new nucleus, it is called two nuclei combines to form one nucleus. So what is happening? Fusion is happening. So it is nuclear fusion. So once one nucleus splits into two nuclei, it is fission. Fission means breaking up. So one nucleus breaks into two nuclei. Fusion means combining. Fusion means two things fusing together, binding together to form one unit. So two nuclei combining together to form one nucleus. So, and that's a new nucleus. So it's nuclear fusion. Transmutation means transformation. So mutation, the word mutation means transformation, change. Okay, so in genetics also mutation, the word mutation is very commonly used. So transmutation, nuclear transmutation, by the name you can see, it is change of one nucleus into another. Okay, so transformation of one nucleus into another, it is called nuclear transmutation. Fine. So question number 15. If the radioactivity of a radioactive element gets reduced to 1 by 128 of its initial value in 20 days, then what is its half life approximately? So now in this case we have the time given and the ratio given. So what can we calculate from this? We can calculate the decay constant. Okay, it's the same formula we'll use what we have been using till now. We'll solve for lambda first, and from lambda we can solve for the half life. Okay, so the ratio is given as 1 by 28. So n by n0 is given e raised to the power of minus lambda t. So t is given as 20 days. Let's see how we'll solve this. N by n0 is equal to e raised to the power of minus lambda t. So n by n0 is given as 1 by 128. So 1 by 128 is equal to e raised to the power of minus lambda into 20. 20 days is the time given. So minus 20 into lambda. So if you have to solve for lambda, you will take log on both sides. So natural log of 1 by 128 is equal to minus 20 into lambda, or natural log of 128 would be equal to 20 into lambda. So you solve the natural log for 128 and then divide it by 20. So you will get the answer to be 0.24. The value of lambda is 0.24. So 0.24 days inverse. Why days inverse? Because the time was given in days. So days inverse. Now once you have the lambda, what do you have to do? We have to calculate the half life. So how do we calculate half life? Half life is nothing but 0.693 divided by the decay constant. So you have the decay constant lambda as 0.24. So 0.693 divided by 0.24, it is equal to 2.89 days. Okay. I hope there is no doubt in this question, the calculation of this question.
No doubt.
Yeah. So the answer is option number D, 2.89 days. Okay. So we'll move to the next question now. Question number 16. If half-life of radon is 3.8 days, then approximately how much radon out of 40 gram will be left after 17 days? So 3.8 days is the half-life of radon. How much radon will out of 40 gram will be left after 17 days? So the initial amount of radon is given as 40 grams. We have to find the final amount of radon, and the half life of radon is given as 3.8 days. So again same formula we can use. So half life is given, so we can calculate the lambda value, the decay constant. So the decay constant is 0.693 divided by T half, that is 0.693 divided by 3.8. 3.8 days was the half life, so 0.693 divided by 3.8. So the lambda value, that decay constant value, is 0.182 days inverse. Now again n is equal to n0 e raised to the power of minus lambda t. So your n0 initial value is 40 grams, 40 into e raised to the power of minus 0.182 into 10 into 17, because in 17 days we have to find the amount of material left, amount of element that is remaining undecayed. Okay, so 40 into e raised to the power of minus 0.182 into 17. So you can solve this. 0.182 into 17, calculate. So if we calculate 0.182 into 17 would be equal to 3.09, and e raised to the power of negative 3.09 would be approximately equal to 0.05. So if you multiply it by 40, so it will be 1.8 grams. Okay, so that means 1.8 grams of radon will be left out of 40 grams after 17 days. Okay, so half life was given, so we calculated the decay constant, and then from the decay constant we can calculate the rest of the question. All the questions are similar now, so you can easily understand what is the approach needed to solve these questions. I hope this is clear, the calculation. If there is any doubt in the calculation part, you can ask. I can tell again. Okay. So the next question is question number 17. In all radioactive decay, which one is the ultimate stable product? In all the radioactive decay, which one is the ultimate stable product? We have to tell. So thorium, lead, uranium and actinium. So what did I tell you? How do we define stability? After what atomic number the nuclei becomes unstable? I have told you now. What was the atomic number value after which the nuclei becomes unstable?
83.
Yes, 83. So if you see all the other elements, thorium, uranium and actinium, the atomic number is above 83. Only lead has an atomic number below 83. The atomic number for lead is 82. So the answer for this question is lead. The stable product after the radioactive decay will be lead. Okay. So the next question, question number 18. Which of the following is a radioisotope? Now what do you mean by radioisotope? What is isotope? Isotope means the elements having the same atomic number. So same atomic number, like in the in one of the previous questions I have shown C14 and C12. So C14 and C12 are isotopes of each other because the atomic number for both were 6. Okay. So similarly here we have 4 options: C12, P32, Na23, sodium 23, and sulfur S32. Okay. So we have to tell what is the which of the following is a radioisotope. Now isotope we understood. What do you mean by radioisotope? Radioisotope means the isotope that is possessing radioactivity. Okay, that is radioisotope. So in this question, if you see carbon 12 is not a radioisotope. It's the most commonly found form of carbon, the atomic mass 12. So it is not radioactive. C12 is not radioactive. We know that most of the things around us in nature are made of C12. P32. What is the atomic mass of phosphorus? The atomic mass of phosphorus in the periodic table you must have seen as 31. Okay, so P32 is an isotope of 31, P31, that is generally found. So P32 is actually radioactive. So it is used in different forms of radioactive labeling studies. So if you have to see the which phosphorus atom is getting incorporated, or if you have to label something and track its movement, so you can always tag it with P32. You can change the phosphorus in that with P32 and you can check the radioactivity. Okay, so P32 is actually radioactive. So the answer for this question is phosphorus 32. Sodium 23 and sulfur 32 also don't have any radioactivity. Radioactive form of sulfur has the atomic mass of 35. So S35 is generally the radioactive form. Like P32 we have S35. S32 is the most commonly found form of sulfur. Okay. So the answer is P32. Moving to the next question, question number 19. Initial mass of an iodine isotope was 450 grams. Determine the approximate mass of iodine after 40 days if the half-life of the isotope is 8 days. Now again, how do we solve this question? We have the half-life given, so what can we calculate from this? If the half-life is given, yeah, tell me.
We can find the value of lambda if T half is given.
Yes, so from
Yes.
T half we will find the value of lambda. So lambda will be 0.693 divided by t half, that is 0.693 divided by 8. Now we have got the lambda. What to do next? What do we have to calculate? We have the initial mass of iodine as 450 grams. We have to find the final mass of iodine. Yes.
N equal to N0 into e to the power minus lambda t.
Yes.
Lambda is already known and t is given.
Yes. So
No, N0, yes, t is given.
T is given
Determine
and
the approximate. Yes, yes.
N0
And
is also given.
N0 is given. N0 is given. Yes.
So we have to find the N. Okay. So let's see. So N is equal to N0 e raised to the power of minus lambda t. Lambda is equal to 0.693 divided by the t half, that is 0.693 divided by 8, that is 0.0866 per day. Now N0 is given as 450 grams, lambda is 0.0866, t is given as 40 days. So now when you solve this, so you can easily multiply 0.0866 into 40, it will be 3.46 approx. So 3.46, if you take the power of E as negative 3.46, it will be approx equal to 0.03. So if you multiply 0.03 by 450, you will get the answer to be 14.09. Okay, so the amount of iodine isotope that is present after 40 days is 14.09. Option number C, 14.09. From 450 grams of iodine, 14.09 grams of iodine will be left after 40 days. Okay. So this is clear. Option number C is the correct answer. So the next question number 20. After 17 hours, only 0.35 grams out of an initial quantity of 1 gram of radioisotope remains. Its approximate half-life is. So now 0.3 initial amount was 1 gram. Final amount is 0.35 grams. So now N is given, N0 is given. Time is given as 17 hours. So again we can calculate the lambda value first. Once we have the lambda value, we can calculate the half-life. So 17 hours. So 0.35 grams is N, right? So N is equal to 0.35 grams, which is equal to N0, that is 1 gram, e raised to the power of minus lambda into t. T is 17 hours. Okay. So 0.35 grams is equal to e raised to the power of minus lambda t, that is 17 hours. So if you try to solve this, so here in this solution again they have used a more direct approach actually. So if you use this formula 1 by t log n0 by n. So basically they have converted natural log into log base 10. So for that we can multiply it by 2.303. So lambda is the decay constant, t is the time elapsed, so time is given as 17 hours. A here is n0 basically. N0 is the initial quantity and n is the final quantity. So you can find the lambda. Once you find the lambda, you can easily substitute the value of lambda in the formula of T half. T half is nothing but 0.693 divided by lambda. Okay, so 0.693 divided by 0.06, it is coming to 11.55 hours. So half life of this radioisotope is 11.55 hours. That is option number A is the correct answer for this question. Okay. So this was clear.
Will you show the answer again? So if we adopt the direct approach, is there any problem?
No problem. So you can directly use the formula. So let's solve using that formula also.
Yes, it is coming also. Lambda is 0.0617 in my case.
Yeah,
If
and then you
yeah,
can divide it with 0.69. So it's fine. It's
yes, yes,
actually the same formula. So if you see,
yes.
n is equal to n0 e raised to the power of minus lambda t, right?
Mm-hmm.
So if you
Yes,
take the n0 towards left hand side, it will be n divided by n0 is equal to e raised to the power of minus lambda t. Okay, then
yes,
if you take
yes,
log both sides, so it will be log n by n0 is equal to log e raised to the power of minus lambda t. When I am saying log, I mean natural log. Okay, ln. So ln
yes,
n by n0 is equal to ln e raised to the power of minus lambda t. So that ln e raised to the power minus lambda t will be equal to minus lambda t, because anything in power will come outside of the log. So you will get the answer to be ln n upon n0 is equal to minus lambda t. Okay, so that means
mm,
if you
yes,
take the negative sign on the other hand, on the left hand side, so it will be
mm,
ln n0 by n, that is initial divided by final, is equal to lambda
mm,
multiplied by t.
mm,
That
yes,
t, when you take it to the left hand side, so that means 1 by t ln n0 by n is equal to lambda, and then you
yes,
can just convert ln into log. Okay, so to
mm,
convert ln into
okay.
log, they multiply it by 2.303. So
Okay,
this
but
formula
instead of
is
converting, actually, instead of converting it into
yes, it is.
a log by multiplying 2.303, if directly in calculator we use ln also, we are getting the answer.
Yeah. You can easily get that answer. There's no problem. So I'm
Yes,
just saying that this formula is nothing but derived from that formula only. It's not a new formula.
yes, yes,
Okay. So
yes.
you can use any
Mm.
formula that you are comfortable with.
Okay.
So any doubt at any of the questions previously discussed?
No, no, but
Okay. So in this session, mainly you have to remember that one formula, n is equal to n0 e raised to the power of minus lambda t. If you remember that, and another thing is lambda is equal to 0.693 by t half. These two things, if you remember, I think you will be able to solve the rest of the questions, all the numericals at least. So numericals are based on majorly these two formulas only. Apart from this, the major things that you have to remember is what is alpha particle, what is beta particle. So alpha emission and beta emission, what is happening. So in an alpha emission, alpha particle is equivalent to an helium nuclei. So in an alpha emission, atomic number will decrease by 2 and mass number will decrease by 4. In an beta emission, the atomic number will increase by 1 and the mass number will remain unchanged. So these things, when you remember, I think it will be easier for you to solve the questions of this topic. Mainly that to solve all the numericals, the formula n is equal to n0 e raised to the power of minus lambda t, that is the most important part.
Yes, it is clear now.
Yeah. So I'm just going through all the slides once more, you can see, and then we can end this session. Okay, then if there's no further doubt, then we can end this session now. Thank you.